So hello everyone, I'm Hugo Lefebvre, PhD student at the University of Manchester. And in this talk, I will present the result of my research on compartment interface vulnerabilities. So before starting to talk about interface vulnerabilities, let me bring a little bit of background. And an important notion in this work is that of compartmentalization. And compartmentalization is about decomposing software into lesser privileged components, such that components only have access to what they need to do their job. And compartmentalization is not something new, but a lot has been going on in recent years, so let me illustrate that. Let's say we have an application that might be pre-existing or being developed. What compartmentalization does is identifying a particular component that may be untrusted or risky or trusted and critical, and separating it automatically or semi-automatically. Since the components are generally not fully self-standing, they continue communicating over messages or shared memory. The granularity of components can be very variable, ranging from libraries to blocks of code. Notice that I'm talking about compartments here, not processes, as the isolation technology too is very variable. In recent years, there has been a lot of compartmentalization research with an increased focus on legacy software, compartmentalizing at increasingly fine granularities as enabled by new mechanisms, targeting increasingly internal boundaries, and with all of this, automating more and more process that used to be vastly manual. So in short, we have very ambitious trends that envision to compartmentalize legacy software with a low engineering effort and at a low performance cost. Unfortunately, as we're highlighting in this work, things are not quite as easy as they might seem. In privileged separated software, cross-component interfaces are the attack surface, and there all sorts of things can go wrong security-wise. So let me give you a few examples. Let's say we have two compartments, one on the left that we deem to be malicious, and the other one on the right, trusted, protecting some sort of secret. The compartmentalization mechanism is going to guarantee us that compartment 1 cannot access compartment 2's memory directly, so doing something like this wouldn't work. However, compartment 1 is still able to do legitimate API calls to compartment 2 with, for example, an invalid pointer. If compartment 2 does not validate the pointer, it will risk exploitation. Another example is the usage of corrupted indexing information, for example, the size, index, or bounds, as is done in this function. Another one is the usage of corrupted objects, such as a tempered file pointer. And there are many others which we'll partially go through in the next slide. In this work, we unify all of these vulnerabilities under the concept of compartment interface vulnerability, or CIV. CIVs encompass traditional confused deputies, IAGO attacks, which are specifics to the system call API, and their references under influence, and probably many others. They are all attacks revolving around misuse of a legitimate interface. CIVs are very common when compartmentalizing unmodified applications, and they affect all compartmentalization frameworks because they are a fundamental part of the problem of privilege separation. So to put it in more precise words, we define CIVs as the set of vulnerabilities that arise due to lack of or improper control and data flow validation at compartment boundaries. We observe three classes of CIVs: data leakages, data corruption, and temporal violations. Within data leakages, we differentiate between address leakages, which can be leveraged to de-randomize compartments and mount further attacks, and compartment confidential data leakages, which result in information disclosure. Both are due to data oversharing or sharing of uninitialized memory. We have already illustrated a range of data corruption attacks in the previous slide, but generally, they are bound to happen in situations where interface crossing data is used without appropriate sanitization, and they can affect control as well as non-controlled data. Finally, temporal violations include vulnerabilities like expectation of API usage ordering, or usage of corrupted synchronization primitives, or shared memory time of check to time of use. Temporal violations are usually caused by a wide range of behaviors, including missing copies, double fetches, and generally lack of enforcement of API semantics. This is a broad and very succinct overview, but the paper provides a full taxonomy, including an analysis of existing defenses. So having observed and characterized the problem, we asked a few questions. How many CIVs are there at legacy and ported APIs? Are all APIs similarly affected by CIVs? For example, if I take library APIs versus module APIs in general, do I observe systematic differences? How hard are these CIVs to address when compartmentalizing? And how bad are they? If you don't fix them, maybe because you decided not to or because you overlooked some of them, what can attackers do? We believe that it is really critical to understand these points to be able to provide countermeasures that are adequate, systematic, and usable. And so the approach that we took in this work is to design a tool, and more particularly a fuzzer, specialized to detect CIVs at arbitrary interfaces, and we called it ConfFuzz. We applied ConfFuzz at scale to a range of applications and interfaces to gather a data set of real-world CIVs. And finally, we studied, systematized, and patternized the resulting data set to extract insights on the problem of CIVs in compartmentalization. In the next slide, I will give you a quick overview of ConfFuzz before focusing on the data set and insights. So let me give you a quick overview of ConfFuzz. Taking modified applications, we instrument them to intercept cross-compartment calls, and here compartments can be freely defined, for example, a particular library boundary or an internal component interface. We based our prototype on dynamic binary instrumentation using Intel PIN, but also explored other instrumentation approaches like LLVM-based. And the interface between the trusted and untrusted components is automatically detected using binary debug information. Our fuzzing monitor then drives the exploration by ordering mutations of the data flow to simulate attacks from the malicious compartment. The workload used to drive the program is application-specific, for example, benchmarking tools, test suite, custom workloads, or you could even plug another fuzzer like OSSFuzz there. And finally, the fuzzer automatically triages and stores crash reports, and that includes deduplicating, reproducing, minimizing, etc. The paper provides more details, and I'm happy to answer questions in the Q&A. So using ConfFuzz, we gathered a substantial data set that we carefully dissected, and here you can see the paper's big table that summarizes the data set. So let's have a closer look at it. Overall, we applied ConfFuzz to 25 applications and 36 APIs for a total of 39 scenarios. And we considered a selection of library APIs, module APIs, and internal component APIs, trying to focus on scenarios that make sense in popular software. In fact, 16 of these scenarios have been previously considered by about 12 studies in the literature and the attacks that we find applying to them. In total, we find 629 CIVs, which we classify in five impact types: to read, write, code execution, memory allocator corruption, and null pointer dereferences. So with this data set, the first questions that we try to answer are how many CIVs are there at legacy and modified arbitrary APIs, and are all APIs similarly affected? And looking into this, the first thing that we see is that CIVs are absolutely widespread among unmodified APIs or code. Having said that, we also highlight significant disparities of prevalence among scenarios, and that's the really interesting part. For example, we observe variation of CIV counts from 0 to 105 across APIs. Take a look at this plot, which represents for each scenario the number of vulnerable API endpoints versus non-vulnerable. It clearly shows that CIV prevalence among applications and APIs is very heterogeneous. We have, on the one hand, large and almost totally CIV-free APIs, and on the other one, small and fully vulnerable APIs. In fact, we show an entire absence of correlation between API size and CIV count in this data set. So while clearly, yes, CIVs are widespread, no, not all APIs are similarly affected. And this motivates us to look into the patterns and effects that influence these observations. And doing so, we observe recurring API design patterns that result in CIVs. And this really comforts us in the idea that the presence of CIVs is influenced by structural properties rather than API size or quantity of shared data. In this talk, I will present one of these patterns, but there are more in the paper. And the particular pattern I want to go through concerns modular APIs. In fact, we noticed that modular or module APIs are the most CIV vulnerable interfaces in our study. On average, we observed that module APIs feature more CIVs and worse CIVs than any other class of APIs. And looking at the structure I'm one too early. I'm sorry about that. And looking at the structure of these interfaces, it makes sense. Unlike library APIs, module APIs must be very generic and yield high performance. And as a consequence, the application's core internal state is exposed to the module. That results in a much larger attack surface exposed to the module. Take the example of this data structure exposed to potentially malicious modules by the Apache HTTPD core. It's very complex with over 75 fields, 60% of which pointers, referencing core data structures like memory pools, connection state structures, or mutexes. What we observe with these patterns is a somewhat counterintuitive thing. Modularity is not always good for compartmentalization, and in many cases it can even be counterproductive. This is only one of the patterns we highlight in this talk, but there are more in the paper. Now, having shown that CIVs are widespread but affecting applications unequally, let's look at their concrete security impact. And the first thing that we confirm is that they are very impactful. Over 75% of scenarios present at least one write vulnerability. Worse than that, about 70% of write and read vulnerabilities and 50% of execute vulnerabilities are arbitrary, which means that when attackers control a write or read primitives, then they are likely to be able to read and write anywhere. And while only a smaller portion of the scenarios have execution impact, it's likely that read and write primitives will be combinable to achieve it. So in this talk, I will be concretely illustrating the impact with practical scenarios taken from the dataset where we demonstrate key extraction from a protected OpenSSL safe box. So here we assume a scenario with two compartments where the goal is to isolate OpenSSL. Thus here the compartment interface and therefore the attack surface is the OpenSSL public API. Unfortunately, we find several CIVs that are able to read and write that enable for read, write, and execution impact. And take this option setting primitive, for example, which is part of the OpenSSL public API. It dereferences an interface crossing pointer, sets it, and returns it, clearly resulting in an arbitrary read and write oracle. Any attacker that can compromise the application's control flow will likely be able to extract the SSL keys easily. Thus, clearly, if the API is not carefully enough sanitized, the benefits will be pretty low, really at much a form of hardening. Now, you could tell me that it's not a good idea to protect at the public API anyways, and that we should rather choose the OpenSSL internal key API that's much smaller. So let's take a look at it. This time we have Nginx and most of OpenSSL in the untrusted compartments, while we have the small key handling part of OpenSSL together with the keys in the protected compartment. Unfortunately, here too we find several CIVs. Take a look at this function of the internal key API. For example, I only put the signature for simplicity's sake because it's written in per-generated assembly. But you can manipulate the in pointer to point to the key that you cannot directly access, encrypt with a known key, and then decrypt to get the secret. Hence here, once again, attackers that manage to compromise the application are likely to be able to easily extract the key. Unfortunately here, fixing these CIVs requires to make the compartment stateful, which is a fairly drastic design change. Overall, through these two examples, I showed how existing OpenSSL isolation strategies collapse when confronted to CIVs and how important they are security-wise. So to conclude this talk, let's take a quick look at the countermeasures. How do we tackle CIVs? Overall, we see two ways. First, making progress on automatic and systematic countermeasures. And our paper highlights their limitations as part of the CIV taxonomy. Second, learning from our study of patterns, we also believe that software component APIs should be designed to feature low compartmentalization complexity in the first place. And we provide a set of guidelines to achieve this. The two approaches are complementary. Even in the presence of countermeasures, well-designed APIs are wishable, as the first point is known to be fundamentally hard. I will not have enough time to go over all the guidelines, but the paper is quite detailed on that. So let me go through it. All right. So we're slowly coming towards the end of the talk. So let me summarize the key points that I tried to make. CIVs should clearly be at the center of every compartmentalization approach. You will likely not achieve tangible security benefits without. API design patterns influence the presence of CIVs and their severity. Overall, it's not so much about the size of the API, it's about the complexity of API crossing objects. And addressing CIVs is not just a matter of writing a few checks. Strong solutions often require refactoring the API, and as a consequence, automatic compartmentalization is really much harder than setting and enforcing bounds. So we want this work to be an appeal for more research towards addressing the problem of compartment interface vulnerabilities, systematically finding them, addressing them, or telling you what interface is a good compartmentalization boundary. If you're interested in this work, I invite you to check out our paper and the code and data set, and I will now be more than happy to take questions. Thank you.
Thanks, Hugo, for the talk. We have time for a couple of questions. So it's very hard to tell who was the first one.
Hi, Evandro de Vera from RIT. Thank you for the great talk. I'm curious, a couple of questions actually, but the one I'm most curious about is how this ConfFuzz architecture changes depending on the underlying compartmentalization architecture. For example, I mentioned something like cherry, right? That works very differently from some other compartmentalization. So how do you deal with the architectural differences?
So yeah, that's a good question. So what we did is we defined some sort of standard compartmentalization model that would be implemented by the different technologies. Of course, their technologies have the specificities, and that's something we capture as part of the taxonomy. Like we made a table going through the different types of CIVs and which technology might address which CIV by design. But otherwise, yeah, we have this standard model of compartmentalization, and we fuzz assuming this model. I don't know if that makes sense.
Hey, Evan Johnson, UCSD. So you presented this taxonomy, quality of types of CIVs. Do you believe that taxonomy is exhaustive, or is it based on just kind of the types of CIVs that you saw in practice? So for example, like if I went down that list, down your taxonomy, prove the absence of all those different types of bugs, how confident should I be that my compartmentalization is safe?
So I'm not sure I completely understood the second part of the question. Regarding the exhaustive part, I cannot make claims on the fact that it's exhaustive or not because I cannot prove it. The second part of the question, unfortunately, I didn't get it. Can you repeat? Okay. Okay. Yeah, it's difficult for me to claim that it's exhaustive. I believe that it's pretty much exhaustive, but I cannot formally prove it. So, thank you.
Hi, Nathan Burrow, MIT Lincoln Lab. Thanks for the great talk. I was curious, a lot of these APIs might not have previously been trust boundaries before we started putting compartmentalization in. Did you look at places where we're doing like input parsing of untrusted input, or places where there was previously a known security boundary? Do any compare and contrast, or just have an insight on that?
Yeah, so indeed, the bigger part of the interfaces that we target, and that actually all these previous studies targeted, were not initially thought as trust boundaries, and yes. However, some of the interface that we targeted were thought as security boundaries, and that was very interesting to look at that. For example, we found a bug in the Nginx worker master interface, which is definitely a security interface, like an interface up to the hardened. So, yeah, there are definitely bugs there as well, and we found some of them, but it is much harder to find because they were designed with that in mind. And yet we still find CIVs there, so.
Hi, Derek P., also from MIT Lincoln Lab. We're here.
Okay.
Would writing a sanitizer, something like address sanitizer or UBSAN, help mitigate a lot of these CIVs by detecting inadequate checks and whatnot as boundary crosses happen?
Yeah, so that's also something that we integrated in this taxonomy. Unfortunately, I realized I should have put it in my talk because that's really interesting. But yeah, they address some of these bugs, but not all of them. Especially some of the bugs that are not read directly spatial memory corruption. They have more subtle bugs, or some timing bugs or ordering bugs that definitely wouldn't be detected by these. So yeah, I might take a look at the taxonomy, and I think I might answer the question a bit better.
Okay, please join me in another round of applause for Hugo.